Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the introduction to moment of inertia. Let us begin with what is moment of inertia and what are the types of moment of inertia. Here, the moment of inertia is nothing but in mathematical expression, it is sigma times AR square, where A is the area of the plane and R is the distance from the centroidal axis of the plane to another axis, where we are going to find out the moment of inertia. Now, coming to the types of moment of inertia, there are two types of moment of inertia. One is based on the geometry. If it is the area planes related to planes, it is known as the area moment of inertia. Area moment of inertia. And the second one is mass moment of inertia. First one is area moment of inertia, and the second one is mass moment of inertia. Area moment of inertia is applicable for a plane geometries or two-dimensional geometries, whereas mass moment of inertia is useful for calculating the moment of inertia of 3D solids or solid objects. So here, the area moment in this session, we are going to study what is area moment of inertia. We consider a moment of inertia. The meaning of moment of inertia in this session is related to the term plane figures, that is area moment of inertia. Now here, consider a plane area. We are going to find out the moment of inertia of a plane area. We are considering a plane area whose moment of inertia is required to be found out. Now we split up the whole plane or plane area into small number of elements, small elements. So the small elements are denoted with area of the small. Each element 1 is A1, element 2 is A2, element 3 is A3, and so on. These are all areas of small elements. Now, and R1 and R2, R3s are corresponding distances of the elements from the line about which the moment of inertia is going to be calculated. Now further, suppose, what is the meaning here? The meaning here is, suppose we consider a plane and we divide this plane into small elements, which are small elements. Now, this is the axis about which this moment of inertia is going to be calculated. Suppose here this 1 is the area, 2 area of this is the second element, third element, fourth, okay, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and so on. And where R1 is the distance of that element, this distance of that element to the axis where we are going to find out, that is R1. Now, the moment of inertia can be calculated, the sum of the product of these areas times A1 element area is the A1 is the element area 1, and to distance about which axis, that is the R1 corresponding R1 square, that is A1 R1 square plus A2 R2 square plus A3 R3 square, and so on. The number of elements, suppose having 100, that means 100 times you have to summation. Then I equal to moment of inertia, I equal to sigma times AR square. This I is the moment of inertia of this plane area. Now, the units of this moment of area, that is, as we have studied, I equal to sigma times AR square. Now, what is the area of the unit? That is square millimeter. Whatever R, millimeter, it is a square, millimeter square. The area, the unit of this area moment of inertia is mm power 4. Okay, now here The moment of inertia of the plane here is depends upon its area and the length. This moment of inertia of the plane is dependent upon two parameters. One is the area and one is r. That the r is corresponding distances of the element about the axis, which is we are going to be calculated area moment of inertia. Now the point is that the area moment of inertia is dependent on a and r, and the unit, if the area is in meters, in square meters, the moment of inertia unit is millimeter in meter per 4, and if the area is in square millimeter and the length is in millimeters, then the moment of inertia is expressed in terms of millimeter power 4. Okay, so the unit of the moment of inertia is square power millimeter power 4 or meter power 4. Now we are going to find out the moment of inertia by integration. That's what we have mentioned in a simple manner, that is sigma, that is AR square. How it is going to be calculated mathematically, here we consider the geometry here. The plane area is arbitrary geometry, and the axis xx and yy are the reference axis. Now dA is the area of the strip, elemental area of the strip, and x is the distance of the center of gravity of that elemental strip from about center x. Y is the distance, where x is the distance of center of gravity, that elemental area, to about y, that is x is the distance about y axis, and y is the distance of the centroid of that element about which axis? X axis. Alright, okay. Now we know that the elemental area, the moment of inertia of that strip about y axis, about which axis? About y axis, that is a dA times x square. Now we want the total moment of inertia of all elements. What to be done? We have to do integrate or sigma, that is Iyy equal to sigma times dA x square. Okay, that is elemental area. And what about Ixx? That is sigma times dA y square. Now about xx, what is the distance? Vertical distance y. About axis y, what is the distance? That is x. That's why here about moment of inertia about vertical axis, that is the distance of the dA elemental area to and x square, dA times x square, sigma dA times x square. And about x-axis, horizontal axis, what is the y? dA times y square. Now what is the area? Unit is millimeter square, and x is the distance, that is millimeter, x square millimeter square. The unit is millimeter per 4. Okay, and similarly, if you want to find out here the two-dimensional, you cannot make it as a z-axis. Alright, it's the two-dimensional, either xy or yz or zx. So we are considering the usual or simple understanding, that is the axis x and axis y, horizontal and vertical. The xy plane we are considering here. The plane we consider is xy plane. That's why about x-axis and about y-axis. So that is Iyy equal to sigma times dA x square, Ixx equal to sigma times dA y square. So thus we have to calculate the moment of inertia by using the mathematical function, that is integration concept. Now let us understand more how to find out the moment of inertia of a simple geometries. There are various types of simple geometries. The simple geometries such as circle, rectangle, section, and square section, etc. And I section also. Yeah, simple geometry, rectangle, square, and circular cross sections. And let us find out. Now we are going to learn the moment of inertia of a rectangular section. How to find out the moment of inertia of a rectangular section. Now before going to start the expression, the moment of inertia of a rectangular section, let us briefly, what are the applications? What is the use of this calculation of moment of inertia in strength of materials or solid mechanics, and where it will be useful, this moment of inertia. Yes, the moment of inertia calculations are highly useful in calculating the bending stress and bending moment, maximum bending moment, and also the modulus of elasticity. Okay, not only bending moment, bending stress, and modulus of elasticity, and also we have to calculate the shear modulus. Okay, shear stress distribution across the cross section of the beams. Okay, and also by using this moment of inertia concept, we have to know how the span of the beams can be calculated, and moment of inertia is also useful to find out the strength of the beams, that is the section modulus. How? Let us give a glimpse of this moment of inertia concept, how it will be useful. Here the moment of inertia, we are talking about moment of inertia is area moment of inertia. Okay, not mass moment of inertia. The area moment of inertia. Okay, applications, as I mentioned, to calculate the maximum bending moment, bending stress, modulus of elasticity, shear stress, modulus of rigidity, section modulus, Z, section modulus, that is the strength of the beam. How? Actually, there is a bending moment equation, the theory of simple bending. In the theory of simple bending, the derived expression is m by I equal to sigma by y equal to E by R. What is this I? I is nothing but here the area moment of inertia, where m is the maximum bending moment, sigma E is the stress, sigma is the bending stress, maximum bending stress or bending strength also calculation, and where E, capital E, stand for modulus of elasticity, where y is the distance from top surface to neutral axis, where R is the radius of curvature. So this I will be useful if you correlate. Yes, m we know, sigma we know, and y. So I can be calculated. If we know the I and sigma, m can be calculated, vice versa. And if you make it part 1 to part 3 equate, this I is highly useful to calculate the modulus of elasticity. This modulus of elasticity is one of the elastic constant. Okay, by knowing the modulus of elasticity, we can find out the strength of the beam. And Z equal to, where is section modulus, Z equal to I by Y. This I is the area moment of inertia. Okay, these are the calculations. So one more thing is that I by Y, that is Z equal to I by Y section modulus. There is from moment of inertia, area moment of inertia, another parameter very important comes as a polar moment of inertia. This polar moment of inertia comes to calculate, find out the shear stress modulus of rigidity. That is the modulus of rigidity. How to calculate, how it will be useful to find out the modulus of rigidity. That is T by J equal to tau by R and equal to T by J equal to tau by R equal to G theta by L. This equation, this expression is known as the torque equation. Yes, we'll study in strength of materials. Where, what is the J? This J is the polar moment of inertia. This J is the polar moment of inertia is connected to moment of inertia I. Where capital T is the torque calculation, it will be useful. Here, the moment of inertia is in domain form, not direct, it is in indirect. That is the J. Torque can be calculated. The torque, the shear stress, and modulus, where G is the modulus of rigidity, and L is the length of the beam, where theta is the angle of twist. All these things can be calculated by using what? Moment of inertia concept. And the moment of inertia is highly useful to calculate the section modulus. Why section modulus is important? If the section modulus is high, the strength of the beam is high. That's why based on the value of the section modulus, we'll choose, or the area of the cross section of the beam can be chosen, can be selected. The area of cross section of the beam is this I section, or suppose if there is a table, the table is having vertical columns. The table is having vertical columns. What is the cross section of these vertical columns? Is this rectangular? Is this square section? Is this C type or angular L section? What type of section? And suppose in industries, there's a vertical columns will be there. The columns are what type of sections? Made of iron or made of some material, made of metals. What type of section you have to choose based on the applied load. If the applied load is high, the load bearing is high, then what type of section you have to select based on the parameter, that is the Z, section modulus. That's why the bars are I section, C section. If you go to rail track, the rails are in I section shape. Why I section rails? Why not C section rails? Why not Z section rails? Because I section is having more section modulus and more strength. So the capacity to bear the load by train by these rails are very high. That's why section modulus required a high value. That's why this I section geometry was chosen for fabricating rails, loco rails. You like that? That's why this importance of I section is very, very important. Here we are going to calculate how to derive the expressions, suppose for a rectangular section, and how to calculate what is the expression of moment of inertia for this rectangular section. Alright, with this brief introduction, brief discussion about the importance of the moment of inertia, especially area moment of inertia, we are going to start to calculate the moment of inertia of a rectangular section. Okay, now the rectangular section is having the width B and the depth D. Okay, and here the rectangular section is denoted by various letters, that is A, capital letters A, B, C, D, corners, and axis XX and axis YY. These are the axes passing through center of gravity of the rectangular section. The center of gravity of the rectangular section about XX in vertical, that is D by 2 and B by 2. Okay, location of this. Now we are going to find out the moment of inertia of this rectangular section about moment of inertia about centroidal axis, or the axis passing through the center of gravity is the neutral axis. Is the horizontal and vertical also. It is about XX we are going to calculate. And similarly, the same methodology can be applied for calculating the moment of inertia about vertical axis YY also. But here we are going to calculate the parallel to axis about centroidal axis. Now the area of the strip, so we have to find out the elemental area. The elemental area is denoted by PQ. Okay, the strip elemental area is actually distance of the thickness of this elemental area is the dy, width is the b, so b dy is the elemental area of the strip. Now we know the moment of inertia of the concept, moment of inertia of the strip about x-axis, that means dA times the distance from x-axis to elemental area, that is y, dA times y square. So what is the dA elemental area? dA is b dy. This is b times elemental thickness dy times y square, b y square dy. We want to total all elements about axis, then we have to integrate. How to integrate? The integration is that minus d by 2, it is minus d by 2 plus d by 2, the total. So the limitations, minus d by 2 plus d by 2, b dy, that is b y square dy. So that is Ixx. B is the constant width. What is the variable here? Y square. So b times integral minus d by 2 plus d by 2 y square dy. b times, what is the y square dy integration? That is y cube by 3 minus d by 2 plus d by 2. So b, substitute here, b times, what is the y value here? Substitute d by 2 cube time by 3 minus of d by 2 cube by 3. So if you simplification, if you do b times here d cube by, what is the value here? 2 times the 2 cube, 2 2s 4 2s 8, 8 by 3, 24 minus, this is negative plus, that is d cube by 24. Now that is a b d cube by 24 2 times, that is 2 d cube by 24. 2 how many times? 12 times. That's it. We got it as b d cube by 12. So thus obtained this relation, that is b d cube by 12. Okay, this is about axis xx. If you want to find out, this is about ixx equal to, from this ixx equal to b d cube by 12. This is the moment of inertia about axis, horizontal axis xx. Now if you want to find out the moment of inertia about y axis, yes, Iyy equal to, now you have to consider the vertical strip. Consider the vertical elemental strip. Okay, this is the elemental strip. We consider here what is the distance from here, that is the x, and it becomes dx. What about width here? D. Width is the d, breadth is b. Okay, what is the elemental area? The elemental area, that is di equal to d times dx. So elemental area d times dx. What do we know? Iyy equal to, the concept I'm using here. Okay, here how to get it? Elemental area dA equal to d times dx. Now Iyy equal to x dA, x square dA, or dA x square, d times dx, that is x square dA x square. That means d times x square dx. Now if we integrate, minus b by 2 to plus b by 2. Then if we do it, then what happens? X cube by 3. Then what will happen here? db cube by 12 can be obtained. Okay, db cube by 12. So you apply it here, that is x cube by 3 after integration. What will happen here? That is db cube by, just wait, we are going to show you. Iyy equal to d times x cube by 3, that is minus b by 2 to plus b by 2. Now d times b by 2, that is b cube by 24 minus of minus plus b cube by 24. Then it becomes d times 2 times b cube by 24, 12, then db cube by 12. So Ixx equal to bd cube by 12 and Iyy equal to db cube by 12. These are the important expressions of moment of inertia of a rectangular section. Now we have to apply those expressions to calculate the moment of inertia about xx and yy. Now here about Ixx centroidal axis, this Ixx is passing through the center of gravity of the section. Okay, that's why Ixx here. So that is b times bd cube by 12. IYY, that is dB cube by 12. After knowing these expressions, we have to remember, after understanding and memorize also, and we are going to apply by taking as an example of your by example. Now find the moment of inertia of a rectangular section is having 30 millimeters wide, that is B equal to 30 millimeters, and 40 millimeters depth, D equal to 40 millimeters. We have to find out the moment of inertia about axis XX and YY. Alright. Now we already derived for the same data expression for rectangular section. The derived expressions are Ixx equal to BD cube by 12 and Iyy equal to dB cube by 12. Now Ixx equal to BD cube by 12, substitute in the place of B as 30 millimeters and D 40 millimeters. Substitute over here, and B, that means 30 times B, D is 40 cube by 12. Whatever D, 40 times, whatever Iyy, B, 30 cube by 12. That's it, simple. Substitute here, 30 times 40 cube by 12, that is 160 times 10 cube millimeter power 4. And whatever Iyy, that is dB cube by 12, where D is the 40 millimeters and B is 30 millimeters, 30 cube by 12. Then 90 times 10 cube millimeter power 4. Ixx, Iyy. These are the moment of inertias. We calculated here mathematically. Now, Ixx and Iyy, the values are, now let us interpret more and more. The value of Ixx is greater than the value of Iyy. Why here? Here, the depth, the BD cube by 12, the depth is more, larger value in the case of Ixx, whereas the B is affecting cubical, the cubical form, that cubical here it is, B is the B cube here, the value of the B is smaller, that's why Ixx is greater than Iyy. Now, if suppose, now rectangular section, rectangular not only here, the vertical portion, this is also rectangle. For this case study, Ixx and Iyy, now D becomes, now whatever D, the D becomes here, the D is smaller. For this case, for this rectangle, the D is here and B is value. For this case, which value is the larger value? Is this Ixx or Iyy? For this case study, Iyy becomes greater than Ixx. Why? The width B is larger value in comparison to the depth of D value for this case study. So we have to be careful and cautious what to substitute, what is the D, what is the B, and about which axis we are going to calculate, about XX or YY. So unless and until you know the concepts, then the expressions, we can substitute in the expressions in a right manner. So far we calculated a solid rectangular section. Suppose if there is a hollow rectangular section is there, then what is the moment of inertia for hollow rectangular section? Yes, the hollow rectangular sections, the outside there are two things, outer dimensions and inner dimensions. The outer dimension of the hollow rectangle is the depth D and breadth wide dB, breadth B. And what about inner rectangular? Depth D1 with B1. The outside rectangular section is substituted is marked as ABCD, inside one is EFGH. No need to go for all these concepts of expressions. We already know the solid section, the moment of inertia of a solid section. What we are going to do it as, we are going to subtract the larger from the larger value to inner smaller. How it is here, about Ixx, parallel to XX, that is B d cube by 12. From that you subtract the smaller one, that is B1 D1 cubed by 12. This is the derived expression for the moment of inertia of a hollow rectangular section parallel to x-axis. About y-axis, again dB cubed by 12 minus d1 b1 cubed by 12. These are the expressions or moment of inertia of a hollow rectangular section. Let us see here. Yes. Then if you substitute it, then we'll get the solid one. Alright. Solid one you have to. Then we get it. That is b2 cubed by 12 minus b1 d1 cubed by 12. And here, one more thing. Now, here for this case study, IXS is larger, greater than IYY. For this case study, why? The depth of the D value is greater than B value. Okay. D value is greater than B value. That's why here the axis value is greater than IYY. Moment of inertia about y-axis. Now, very important is that the moment of inertia is dependent on two parameters. One is B and the other one is D. In the case of the concept of moment of inertia, A or square, here the area of cross section and here it is the distance, correspondence distance. Here also 2. From this derived expression we got this we derived this hollow circular section. That's why in this case here the depth and the breadth of the sections is dependent. So starting it is two parameters, area and the corresponding distance. Now here are also after derived expression also it is dependent on two parameters only. Okay. Now this is the moment of inertia of a hollow rectangular section. Suppose how to solve this hollow rectangular section. Okay. How to calculate, how to find out the moment of inertia of the hollow rectangular section. Provided if you know the depth and breadth values of a hollow rectangular section, here the D value they mentioned. If we know the D value and the B values, D is 40 millimeters, B is 30, and here it is D is 20, and breadth B1 is 10. Okay. Then what will happen? We know substitute here IXX comes, substitute B and D values, B, D and B1, D1. You can directly obtain the moment of inertia about x-axis and y-axis. Okay. This is our the brief introduction. In this session we studied the introduction of course, the introduction, what is the moment of inertia and the types of moment of inertia, what is the use of values of moment of inertia, why to calculate moment of inertia and importance of moment of inertia, and we used the integration method and we derived the expression of a rectangular section's moment of inertia, and we used the concept of rectangular section of moment of inertia and applied it to the moment of inertia of a hollow rectangular section, and also derived expression of hollow rectangular moment of inertia of a hollow rectangular sections about axis IXX and IYY, and also calculated the moment of inertia of a rectangular section and applied in order to understand more and more the concept of moment of inertia of a rectangular section. Further, we solved the problem of a rectangular section and found the moment of inertia for that section is having a depth of 40 millimeters and breadth of 30 millimeters. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.